I wanted to tell you about the TAOS, Texas Advanced Optoelectronic Solutions programmable color light to frequency converter. And you may have seen it, you may have heard about it, you may have even built something on it, but I'll tell you, this is a really cool chip. And what I did is I bought the OSEPP breakout board for it, and I'll show you that in a second. But I wanted to show you the chip first. And it is, it basically turns color into a frequency that you can then count. You know, you can send to an Arduino or whatever microcomputer that you want to count that frequency, and then you can scale it however you want, and then determine the color that the sensor is detecting. And you have two control signals, S2 and S3, that determine which color, red, blue, or green, or clear, that you're looking at. So you can work your way through those, get your three primary colors, and then establish a real, you know, a compound color, I think it's called. Programmable color and full scale output frequency. You can change that to be lower or higher frequencies. So depending on your microcontroller, you can have it count. If it can't count that fast, then you know, if you got a slow clock rate on your microcomputer or your Arduino, say, or whatever, then you can slow down the frequency output as a reference to the color that it's seeing. And let's see, anything else interesting on this first page? There's the chip. And I am getting as soon as I get my microphone in, I'll be doing screen capture, so you won't see these lines anymore through there. I won't be filming directly off the screen. Thank you for putting up with that for me. I do appreciate it. I don't think you can read that, but it's the TCS 3200, a light to frequency converter, reads an 8x8 array of photodiodes. 16 photodiodes have blue filters, 16 have green, 16 have red filters, and 16 are clear with no filters. So you can read, so that's how they've got it set up, so you can read each one of the colors. And the four types of photodiodes or colors are interdigitated. You know, I've never heard of that word, interdigitated. I like that. To minimize the effect of non-uniformity of incident irradiance. All photodiodes of the same color are connected in parallel. Pins S2 and S3, that's the ones we just mentioned, are used to select which group of photodiodes, red, green, blue, or clear, are active. Photodiodes are blah, 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 just gives the size, 110 micrometers in size, and are on 134 micrometer centers. It is, and they have instead of moving the camera, I'll move this up. There's just a little block diagram of it. Current photodiode array, and then they have a current to frequency converter. Well, I have it, oh, and here's the chart that tells you where you want ground. You want ground, your output enable, which is active low, your frequency out, and then S0, S1, which is your scaling. That says, you know, you're going to put out a high frequency, a medium frequency, or a low frequency, depending on your colors. Right now I've got mine set to the high, so I've got both of those set to low, I believe. And then S2 and S3, I have those both set to high, I have those both set to low, which is red, and then your supply voltage. And this is an exciting chip. This is really exciting. And here's the red is S2 and S3 go low, and that's, you're picking red. So that's the group of photodiodes that you're picking to sense off of. And I've got S0 and S1, I've both got set to high, so that my output frequency scaling is going to be at 100%. It's going to be as high a frequency as it can put out for those. Well, I have it hooked up, so let's go look at it. Here it is hooked up, and the The wiring, there's no use really showing you the wiring. I've just got those set to, you know, highs and lows, zeros and ones, and then the ground and the VCC set to 0 and 5 volts. In order to set it up for red sensitivity, it's reading the red group of photodiodes, and it has these clear, as you see, I just blinded you. It has these clear LEDs to emit light and reflect off something. Well, what does that do for you? I've got a scope probe, as you can see here. The scope probe is, I've got it put on the frequency out. And look what our output is. This is our output. So I've just got him sitting in free air. He's set to red. Is what the photodiode group that he's looking at. I'm wearing dark clothes right now, and he's pointed kind of at me, and he's putting out, according to the oscilloscope, he's putting out about 65 kilohertz. And as you see, as I'm going to bring my hand in, and you can see him change frequency as I bring my hand closer to it. So, you know, my hand's going to be more of a reddish hue as compared to the dark clothing I have on. So there he's 74, 75, 76 kilohertz. I take my hand away. He drops back down to 60, 61, 59 kilohertz. So pretty sensitive. So I can, through that, I can determine at least a piece of information to determine what I'm looking at when I'm examining something. So this would be something useful for the robot to examine its environment. It would be just a piece of information that would have to go along with other stuff, other data, in order to fully determine what it is it's looking at. Now let's pardon my reach over, but I'm going to, as you see, I got up away from it. It's no longer looking at me, so it's gone down considerably, down to 37. So now it's not bouncing off me anymore, and it's gone to 37, 38 kilohertz. And let me bring that in. Oops, frequency in. Get a better view of it. So yeah, now we're at 38, 39 kilohertz. Now is that better if I turn that light off? Does that show up better? Maybe. And now I sit back down in the chair where the lights from the unit are pointed at me, and the frequency goes up. So it's detecting some form of red on me. In order to do that, there's, of course, there's going to be all kinds of mixtures of this. There's nothing but compound colors all around us, so there is no pure red, green, or blue. Let's go to blue and see what he does. So we've seen a range anywhere from about 35 kilohertz to 80 kilohertz on the red frequency, just goofing off, just pointing him in different directions, not really pointing him toward something of a particular color. And in order to do that, let me put the switches. I need to put the S2 and S3 to S2 to low and S3 to high. Okay, now I've got him set to look at the group of blue photodiodes, because S3 is high and S2 is low. So that's the blue set of photodiodes. And what do we got there? Just looking at my shirt, which is kind of bluish, it's kind of a dark blue, he's setting at 30 kilohertz, right around 30 kilohertz. Now if I get up, as I did before, we would expect a drop in frequency as we did before. Okay, he goes down to 17 kilohertz. Okay, so we have, when we're set to blue, he goes from 17, just in open air and reflecting off, you know, something that's not particularly blue, like my shirt, just a little bit blue. He's going from 17 to 30 kilohertz. When we had him at red, he jumped all the way from 35 to 85 kilohertz. that is really interesting. Now if we go to green, now if I go to clear, I'm not quite sure of the purpose of clear. That's going to let all that's going to let all the colors in. But let's don't do clear yet. Let's do green. We did red, we did blue. We got the frequencies of those. Let's do green, which is high and high, which I can do with the camera on, because I've got it right here. Okay, now S2 and S3 are both high. And looking at me, my shirt, we're seeing a value of about 27 kilohertz. If I get up, walk away from it, we see him go down to about 17. So he doesn't really change a whole lot. The blue and the green doesn't really change a whole lot, just based on this very non-scientific pointed at me kind of thing. Now if we have something that really is blue, well, these are kind of blue. These right here. That's blue. Yeah, I guess that's blue. If I point this end at him, I'm going to point this end at him. And let's see. Now I know he's on green, and we'll switch back to blue. He's on green. Look at that, he doesn't change much. He goes from 27, there's nothing. I put him right in front of him where he's reflecting right off of that, and he goes up to about 30. So it really doesn't change much there, which is what you'd expect from a really good filter. So if we go back to blue, okay, now we're back to blue again. We're back to S2 is low, S3 is high, so we're back to the blue set of photodiodes. He's not looking at the blue object I have in my hand. He's sitting at about 30 kilohertz. That's just looking at me. Now if I show him the blue object, particularly, get it right up there, right where I had it when it was green, look, he jumps all the way up to 47, 45, 50 kilohertz right in there. Because I can't hold it that steady right in front of him. So there he is at 50 kilohertz. So he's 30, 20, almost doubling his frequency from just looking at out into space to putting a blue object in front of him. He doubles from about 26, 27 kilohertz all the way to 51, 52 kilohertz. Now isn't that interesting? So he really detects that blue. Now if we go to clear, what happens when we go to clear? That's a mystery to me. I don't know. I'm not sure what I know the purpose of that, other than just a light detector, just any color. I mean, that would be the obvious thing. Clear would be, I need to switch S3 and S2. That's easy enough. And now I have S2 high and S3 low, which is clear. Now we're looking at a clear filter. Now, to clear filter, now does that mean he's looking at all groups? Or, how did I read that? Hang on a minute. No, there is a set of photodiodes specifically for the clear filter. It doesn't combine the three. I was thinking there for a second, maybe it combined the three or something like that. But no, there is a set of photodiodes that are specifically clear filter. And I'm just sitting there into open space, it's sitting at 61 kilohertz. When I move around, 64 kilohertz, doesn't really matter. I get up, 64 kilohertz, really doesn't matter. Let me put something blue in front of him. I'll put that same blue object, same distance. Yeah, he goes up to 73, 74, but I'm also reflecting the clear light that's from the 4 LEDs that are around him. I'm reflecting those back onto him, so that may be where that is coming from. That would just more make him a clear light detector not a color detector, of course. But he's sitting at around 62 kilohertz, and if I point him straight up, I'm grabbing him now off screen, I'm pointing him straight up at the ceiling, and he's up at 150, 167 kilohertz. And the ceiling is white, and would that make sense? I guess a white ceiling would make sense, but we need something a little more scientific. I need a white piece of paper. Well, I do have a white piece of paper right here. Boop. White piece of paper. Let me put this white piece of paper and let's test that. Yes, I put that white piece of paper in front of him. That's what he's doing. He's just merely detecting. See, we got him all the way up to 227, 250, 260 kilohertz, 270 kilohertz, through almost 300 kilohertz. And you can see him dramatically move there. And that's just a clear detecting clear light coming into him. And I don't see, I do have a flashlight actually. I have a flashlight. Here's the flashlight right here. As you can see, it's got clear LEDs. Those usually tend to be in the blue, but let's just point this at him and see what happens. Okay, whoa, look at that. Look at that. If I point this right at him, I'm about 8 inches from him, pointed right at him, and we're up around the 800, 817, say 800 kilohertz. We're up around the 800 kilohertz. There's 817 right there. 817 kilohertz, all the way back down to 71 kilohertz. And so, okay, so the clear then just becomes a very sensitive light detector. Well, I don't know, it's a pretty bright flashlight. I don't know how sensitive he is, but I don't know if you would use that as you could turn this on to determine how much light you had in the room. This would be your ambient light source. And see, I'm moving my hand like a teacher does, shaking my hand. This is what you do. And that's the flashlight. So you, nothing against teachers. So what you would do then on your robot is you would set these two values to clear filter, or which is no filter. Get the ambient light in the room, and then whatever you looked at, you could help. That would be part of your reference. Is your ambient light in your room, and say like right now the ambient light is 70 kilohertz. So that would become a value that I would store. You know, from 0 to 255, say, if it was just a byte, if I mapped that to just a byte, then say that would be 70 kilohertz would be 25, the number 25 in there. And then as it got brighter, as the morning came in, and it got brighter and brighter, and then it went up to, the room got pretty bright and it got up to around 200 kilohertz. That might be a value of say 100. And so I know then that the ambient light is 100, and you can do programmatically. Then I can know that if the room is typically at 100, then my red, blue, and green values are I can adjust those accordingly, and I can probably get a better, truer color. I don't know specifically what I'm talking about there, but just intuitively, I think if you have an ambient light level and you have your red, and then you switch over your red, your blue, your green, and your ambient light, then you're going to have really good numbers to work with to get a good solid color of what you've got. And then you could store your three colors as from numbers from 0 to 255, and and your ambient light from 0 to 255, and then that would give you, what is that, 64 million colors or something. Like on a, like the three dots on a pixel of a television. You get 64 million colors out of that. I don't think you'd have a lookup table like that in Arduino, but you could come up with some formulas to help you determine possibly what you were looking at. If you could, when I built a robot in the 80s, one thing I did was when it ran into something different, I didn't have a color detector on it at the time, but I did have a light detector. And when it ran into a different light, it would ask me because it was basically a PC on wheels. An old 80s, if you can imagine, an old 80s PC on wheels with an old a disk drive where it would load up the program. It had 640K memory, I think. And I wrote it in C code, in Turbo C, if anybody remembers that. And it would ask me, what that meant, what the change in light level meant. And then I programmatically, I didn't have a way of telling it. I would have to go in programmatically because it saw something different, and then I would give it a different condition that it saw, and then that condition would mean something, so that when it was there again and saw that again, it could react to it. Then I could program a reaction to it, and that's what I like to do. I like the computer to ask questions in the way that computers do. It can be a light, it can be something on a little screen or something, and then you might have to go in and actually program it in, the difference, or the particular event that you're telling it about, is you programmatically put it in so that it can handle that event, or at least understand it or react to it the way that you want it to. And in that way it would learn, just like a child would learn. A child, of course, is much more sophisticated. A child asks you a question, you answer it, and then you explain it. And I'm getting a charged battery pack. I think I'm about to lose the battery, so I'm going to leave it there. But thanks for listening to this, and we'll come back when we get charged up. Well, I got the battery charged back up, and what I did is I downloaded a program from, let's see, this is for that OSEPP color sensor, of course, the one we're dealing with, by Elect Freaks, by Robbie W. I downloaded a program that he wrote for the Arduino, and, oh sorry, I left you there without the, and it basically, what it does is cycles through the red, blue, and green, as I was doing physically with jumper wires. It cycles through with the Arduino pins through red, blue, and green, and then gives you an output. It does a count. It does a count on each one. It cycles through red, blue, green, does a count on each one, and then prints out the number that it gives. And what you see floating by there is red is about 8,500, green is about 5,000, blue is about 5,200, and the sensor is pointed toward a light bulb, and so that makes sense that red, you're going to have a lot of red in a light bulb. Well, it just made a liar out of me. I pointed it right at the light bulb, and now blue is 14,000, green is 18,000, and red is 16,000. So, oh well, go figure. Whatever that means. I would think there would be more red in an ordinary 100-watt light bulb. Point now. See, there is. I don't know. Maybe it's settling time. Is there? I didn't read that in the data sheet. But now red is 16,000. You got 16, 12, and 13. 16,000, 12,000, 13,000 for red, blue, and red, green, and blue. And those numbers that come up, kind of the 294, those are those are the scaling numbers. I didn't see any commentary in the program what those numbers are, but I think there's something to do with the scale. But anyway, the ones we want to look at are the red, green, and blues. It's a great little program he wrote that counts the, it uses the timer1 include file, which I've used once or twice to time a frequency or to get a frequency. And but he does an interrupt here, and it counts it, interrupts it, and then returns the value, which is really cool. And I like the way he did that. And that's the way you learn. You get somebody who does something like that very well, and that's the way you learn. This is the kind of thing that I would run in the robot, but he wouldn't print them out like this, except under diagnostic purposes. It would react on them in some fashion. You know, I might take 10 samples or something, you know, of red, because I've noticed it does change quite a bit. Take 10 samples and average, do a smoothing average on it of say 10, and so that if something says red, green, and blue, then it's averaged out that way. But I wanted to show you that. We kind of finished up with this particular little neat little device. The OSEPP is where I bought it from. It was expensive. I believe it was $40. I'm not positive that. It might have been $30, but I believe it was $40. But it's based upon the TSC 3200 IC color sensor, and then OSEPP did a breakout board for it. Anyway, I hope you found that interesting. That was great. Thank you.